Today we're going to do 6-1 and 6-5 combo. So let's start with a vector field. What is it? A vector field is simply a function that assigns to each point in the plane a vector. And so this is a two-dimensional vector field, and we can also have three-dimensional vector fields. Down here, I've got an example of a vector field. This is the formula, and below I have a sketch of the vector field, and I want to just show you where those arrows are coming from. So suppose we had to fill out this vector field on our own. If we go to the point 1, 2 in the plane, then we compute f of 1, 2, and that gives us the vector 2, negative 1. And then if we go to the point 2, negative 1, that gives us negative 1, negative 2. So let's plot those. The first one at 1, 2, go to 1, 2 right here, and I go 2 units to the right because x is positive 2, and 1 unit down because y is negative 1, and then that's my arrow. And for the next point, 2, negative 1, I start here, and I go 1 over to the left because x is negative, and I go 2 down because y is negative, and I get that vector, more or less. And the last one at negative 1, I'm going to go 1 to the left and 1 up. And there's my vector. So that's how you would do a vector field by hand. Obviously, we're not going to do that. But when you look at vector fields, you should understand where all those arrows are coming from. And here are 3 ways you can use technology to graph vector fields. I'm going to show you this one a little bit later. But I've got instructions on how to use the other 2. And these are links. Okay, so that's the definition of a vector field. How can we make our own vector field? One way is just to take the gradient of a function. And so we've already seen this when we talked about tangent planes, but let's just look at it again. The gradient vector is the vector of partial derivatives. So, for example, here's a function of 3 variables. So my gradient del f is going to have 3 components. The first component is going to be the partial with respect to x. So that will be 2y will come down to, so 2yz e to the 2xy, comma. Next entry is partial with respect to y. That is a 2x comes down, so 2xz e to the 2xy, comma. Partial with respect to z is easier. It's just e to the 2xy. And so there's our vector field. Okay, operations on vector fields. If we have a vector field in R3, we can compute its curl and its divergence. And in grossly oversimplified terms, divergence measures expansion of a fluid or gas, and curl measures the rotation. But if you want a more detailed explanation, you can go to either one of these sites and find out a lot of information. So let's go back up here and figure out how to compute curl and divergence. You shouldn't memorize the formulas, just memorize how to get them. And the way to do that is to think of del as an operator. Think of del as partial with respect to x, y, and z. And then the definition of curl f would be del cross f. And so I've got my del in the second row and my f in the third row. And instead of multiplication, for example, del by del y, it's not times p, it's del by del y of p. And you can see that right there. Same with divergence. Divergence is del dot f. So you just take the partials that you see here and add them together. And remember, divergence will be a scalar and curl will be a number. All right, let's do an example with this uniform rotation vector field. And I can convert the divergence of a two-dimensional vector field, but not the curl. So I'm going to rewrite this as negative y x 0 so that I can compute both divergence and curl. So the divergence is del dot f, which I have written right here. And unfortunately, there are 2 dels going on because we call the partial derivative signs del 2. So you just have to use context. So this is going to be del by del x of negative y plus del by del y of x plus del by del z of 0. Okay, and each of these partial derivatives is 0. So I'm getting 0 as my answer for divergence. And now let's look at curl. And I've already set up calculation. I'm taking del cross F, and just to save you a lot of writing, I wrote that out there, but now let's compute each of those components. The first one, we've got 0 minus del by del z of x is 0, so that's a 0. The second one is again 0, and the third one, del by del x of x is 1, and then del by del y of negative y is negative 1. 1 plus 1 is 2. So there is our curl, and notice it's a vector. I want to finish by taking a look at this vector field on Calc 3D with you. But before I do that, let me just mention topic 4, parameterizing piecewise smooth curves. This is the parameterization Bible, if you've taken calculus with me, that you saw back in Calc 2. There's formulas for line segments, circles, and functions. And this is going to be super important when we start doing line integrals. So I've got some problems here for you to parameterize, and then the answers are below, so you can check your answers. All right, so now let's hop over to Calc 3D. Here we are, and let's get rid of that function. We can add a vector field by going to Add Vector Field, and the first component of the vector field we were looking at was negative y. The second component was x, and the third component was 0. And we can graph that, and there it is. And if we want to restrict that to 2D, we can do that. And we see a picture that's not exactly like the one on your lecture notes. Notice the arrows are going in a different direction. And that's because for the one in the lecture notes, I had the minus in front of the X and not the Y. But it still gives you the idea of what a rotational vector field looks like. And then the feature I wanted to show you, which I think is fairly new, if you go down here, you can click on curl at a point, and at any point it will compute the curl for you. That is up here. The curl is 2K. Well, that's exactly what we found. And then the divergence at any point is 0. And that's exactly what we found. And you can move this around. And so you might want to play with that. Okay, and that's the end of this section.